So let's walk through the process of how we're going to work conservation of momentum problems. We've seen a couple of examples that hopefully are helping us recognize when we're going to work a conservation of momentum problem. So let's see what the process is for doing that. So for starters, a lot of this process should look very similar because, again, conservation of momentum problems are just vector problems. And so we're going to do a lot of the things that we normally do in working a vector problem. In this case, again, because it's a conservation, that's telling us that we're going from some initial state to some final state. Again, we're going to start by drawing a sketch that shows those two states. So what does our system look like initially? What does our system look like at the end? Then that's going to let us draw out two vector diagrams. So we're going to be able to draw out the initial momentum vectors for all the objects of the system, and then we'll draw out the final momentum vectors for all the objects of the system. As with any vector problem, we're going to pick a coordinate system. We're going to break those momentum vectors up into their components. We're going to set up conservation of momentum equations, and again, we need to set up one equation per relevant dimension in the problem. Then we're going to come back and plug in the magnitudes of the vectors where they're useful. So what will often happen is that we'll set up the problem for momentum vectors denoted with P, though what the information we've been given or maybe what we want to solve for is something with either masses or velocities. And so we'll come back and make that substitution, that P equals mv substitution where it's necessary. And then that'll leave us with a set of equations with some number of unknowns, and we'll go solve for what those unknowns are. So again, all this should look pretty familiar because fundamentally our conservation of momentum problems are just vector addition problems. So let's look at a couple of examples. So for the first example, I've got a block. I'm told it's initially at rest on a horizontal frictionless surface. Another block that I've labeled block 1 is going to slide to the right towards block 2 with an initial speed of 3 meters per second. After colliding with block 2, block 1 bounces back to the left with a speed of 2 meters per second. What's the speed of block 2 as it slides off to the right after collision? Again, the first thing I'm going to do is I'm going to start by drawing initially what does this look like? Well, initially block 2 is just sitting there. Block 1 is sliding to the right with some initial speed that in this case I happen to know is 3 meters per second. At the end, well, now both of them are moving. Block 1 has bounced back to the left with a speed of 2 meters per second, and block 2 is now moving off to the right, and I don't know what speed it's moving at. That's what I'm asked to solve for here. So here's my initial picture, here's my final picture. So now I can set up vector diagrams. And again, you'll notice that I want to make sure that because I'm doing momentum, that I draw momentum vectors. The initial momentum vector of block 2 is just the 0 vector. Block 1 is initially moving to the right, so its initial momentum points to the right. Set up my final momentum vector. The final momentum of block 1 points back to the left because it's bounced back and is moving to the left. And the final momentum of block 2 points to the right. I can pick a coordinate system. So simplest coordinate system to pick is probably the one that I usually use in terms of positive x pointing to the right, positive y pointing up. But again, what I recognize here is that all my vectors lie along that x coordinate, so this is really a one-dimensional problem. I know I want to set up the conservation of momentum, telling me that the total initial momentum of my system is equal to the total final momentum of my system. And again, in this case, that's a one-dimensional problem, so I'm just setting up what's going on in the x direction. Given my choice of coordinate system, I know that the initial momentum for block 1 is going to be positive, initial momentum for block 2 is going to be 0, the final momentum for block 1 is going to be negative, the final momentum for block 2 is going to be positive, and again, what I need to plug in terms of magnitudes is that for all of these blocks, what I'm told are masses and speeds. So I'm going to plug in for the magnitude of the momentum of block 1 initially is going to be m1v1 initial. The magnitude for the momentum of block 1 final is going to be m1v1 final. And the magnitude for block 2 final, its momentum is going to be m2v2 final. So now I can take my table where I've basically broken my vectors up into their components, and again, because it's a one-dimensional problem, mostly that just means taking care of signs correctly, and I can set up my equation. Once I've set up my equation, I can come back, plug in the magnitudes. And so in this case, once I've set up that equation, plugged in the magnitudes, what I see is there's one unknown. It happens to be the speed of block 2 after the collision, so it's V2 final. So when I solve this, I go plug this over to the other side, plug in my numbers, get my solution. So one of the things to emphasize is that, again, there are a couple choices we have in terms of how we could choose to do this. What I'm choosing to do is say, if I know what's going on with directions, then I'm going to go ahead and put the minus sign out front, and so this is the magnitude of that momentum vector, which means this is the speed of block 1 after the collision, not its velocity. You could alternatively choose to work this problem so that you're dealing with the velocities as where you're tucking in the signs. I'm choosing to put the sign out front, and now this is a speed because I've already taken care of the sign and I want a magnitude of that momentum vector. So here's a one-dimensional example. Let's look at a second example where we deal with things sliding in both x and y. So here I've got two blocks that are sliding towards each other on a frictionless surface. Block 1 is initially sliding with a speed of 4 meters per second due east. Block 2 is initially sliding with a speed of 4.5 meters per second due north. After colliding, block 2 slides due east with a speed of 2 meters per second. In what direction does block 1 slide after the collision? Again, notice that what I'm being told here are masses and speeds. So I'm going to end up using my P equals mv substitution to solve for the magnitudes of these momenta. But let me start where I always do, which is let me draw initially what's going on, and I'm told that block 1 slides east, block 2 slides north. They collide, and then after the collision, so at the instant after the collision, I'm told that block 2 is sliding due east and block 1 is sliding off in some direction. I don't know what direction that is. That's what I'm asked to solve for. So I can take my two pictures now and draw my two vector diagrams. So the initial momentum of my system has these two pieces. So there's the initial momentum for block 1, there's the initial momentum for block 2. Because these blocks bounce off each other, my system also has two pieces at the end. So we'll also see there are problems we could work where these two things stick together and I simply have a single piece after the collision. Here I've got two pieces, and so again that means I've got two vectors, one showing the final momentum of block 1, one showing the final momentum of block 2. Pick a coordinate system. In this case, it makes about as much sense as any to let positive x point east, positive y point north. And so now again I want to take these two diagrams and break them up into their components so I can set up my component equation. There's the initial vectors, there are the final vectors. Again, I'll use a table. And so when I look at the equation that I'm setting up, that the sum of the initial momentum vectors, so this is going to be P1 initial plus P2 initial equals sum of the final momentum vectors, P1 final plus P2 final. So again, I've got sort of vector addition on both sides of my equation, and again the equal sign sort of sitting there in my table trying to help make sure I get the equation set up right. So the momentum for block 1 points entirely in positive x, the momentum for block 2 points entirely in positive y, the momentum for block 2 final points entirely in positive x, and I don't know the direction or the magnitude of the momentum of block 1 after the collision, so again I'm just going to choose to leave it in terms of components. Magnitudes, well, I know I can use my P equals mv, and so I do that for the initial momentum for block 1 and block 2, and so I've got P1 initial is m1 v1 initial, P2 initial is m2 v2 initial. I do the same thing for the final momentum of block 2 because again I know its mass and I know what speed it's moving at, but because I don't know anything about the final momentum of block 1, I've left it in components, which means that what I'm going to plug in for the magnitude of those components is going to be mass 1 times the x and y components of the final velocity, mass 1. I can use my table and my magnitude information to set up my equations. Again, because I have a two-dimensional problem, I'm going to set up two equations. So there's the x equation, Again, just using my x column on the left. There's the y equation. Using my y column on the right, I can come back and plug in my magnitudes. So plug in my magnitudes into my x equation, plug in my magnitudes into my y equation. I've used all the information I've got to set up two equations. Two equations, of course, means two unknowns. And so before I go any farther, let me see where those two unknowns are. I'm told the masses of both blocks, so M1, M2, those are known. I'm told the speed that both blocks are moving with initially, and I'm told the speed that block 2 is moving with after the collision. So what that means is my two unknowns are the x and y components for the final velocity of block 1. That means each unknown has its own equation. I can go through, solve each equation for its one unknown. Once I've done that, I can come back, plug in what my values are, and so I get that the x component of the final velocity for block 1 is 0.8 meters per second. The y component is 7.2 meters per second. So if I'm interested in solving for the direction, well, now that I know the x and y components, I can of course use the inverse tangent to figure out an angle. And so in this case, the inverse tangent of y component over x component is the inverse tangent of 7.2 divided by 0.8. And my calculator says that's 84 degrees, given the fact that I have a positive y component which points north, a positive x component that points east. This is 84 degrees north of east. So if I come back to my picture for the final state of my system, block 2 is sliding due east, and block 1 is now making this very large angle, so it's sliding in the direction 84 degrees north of east.